So, good afternoon everyone, and welcome. Thanks for showing up today. What we're going to do today is that we're going to use software evolution as our crystal ball to not only identify, but also to prioritize technical debt. So, let's jump right in and see what this is all about. My starting point is Martin Fowler's well-known definition of technical debt. And I think you're all familiar with this, so I want us to focus on the key aspect. And the key aspect is that technical debt, just like its financial counterpart, incurs interest payments. And I've found that this is something that we as an industry tend to oversimplify and slightly misuse. And the consequence is that technical debt, the concept, is not as useful or helpful as it could be. So let me show you an example. The way I want to do this is that I want us to do a small experiment. I want you to do a small test. So what's going to happen now is that I'm going to show a bit of code for you. And your task is to judge the quality of that piece of code. Are you ready? You do look ready. Here we go. Have a look at this beauty. How many of you will let this through in a code review? It's really just me. Wow. Yeah, of course. I mean, we don't want that kind of code, right? It's a mess to maintain, it's hard to read, and we would never, ever write code like that ourselves. Never, ever. But is it a problem? Is it technical debt? Here's the thing, it's not technical debt unless we have to pay an interest rate on it. An interest rate, interesting enough, is a function of time. So that would mean, in order to uncover a technical debt that really matters, we would need a time dimension into our code. Where can we get such a thing? In a few minutes, I'm going to show you one way. But before we go there, I would like to share a little story with you. So, as part of my day job, I go to different companies. I analyze their code base and I come up with a set of recommendations for them. And earlier this year, I visited one of my clients that prior to my arrival had used one of the tools capable of quantifying technical debt. So they had taken this tool and threw it at their 15-year-old code base. And this tool reported that on your 15-year-old code base, you have accumulated 4,000 years of technical debt. Now, 4,000 years of technical debt, just to put that into perspective, 4,000 years ago, that was here when Moses parted the Red Sea. So, my point is that 4,000 years of technical debt, it may well be accurate, but it's not particularly useful. I mean, where do you start? Is all debt equal? Besides, I think it's a mistake to try to quantify technical debt from code alone. And the reason I say that is because most technical debt isn't even technical. And this is something I find over and over again in my day job, that we as developers, we tend to mistake organizational problems for technical issues. And the consequence is that we address the symptoms instead of the real problems. So you may have noticed that yourselves. A very common case is that someone tells you, hey, watch out with that part of the code. It's so hard to understand, or we have a lot of bugs over there. Or my personal favorite, you might have heard this one, is that we spend a lot of time merging different feature branches. We have to buy a better merge tool. As you will soon see, there may be organizational explanations for those potential problems. And I think the main reason we keep making misattributions like this is because the organization that builds the system is invisible in the code itself. And that's unfortunate because there is a strong link between technical debt and the organization. And I'm pretty sure that we cannot address technical debt unless we take a holistic view of that concept. And that holistic view has to include a social view of our code base. So based on what I've told you so far, I put together a wish list on the kind of ideal information we would need in order to prioritize technical debt. So let me show it to you. The first thing I would like to know is, where's the code with the highest interest rate? The second thing I would like to know is our architecture. Does it actually support the way our system evolves? Are we working with or against our architecture, which is actually quite common? And finally, and perhaps the most important point, are there any productivity bottlenecks for inter-team coordination? You know, those parts of the code where 5 different teams have to work together all the time. Now, if you look at this list, I hope you all agree with me that this is important information that helps us do our job. However, I also want you to note that none of this information is available in the code itself. It's invisible in the source code. Most prominently, we lack some really critical information. We lack a time dimension, like we talked about earlier, and we lack social and organizational information. So how can we get that? Where's our crystal ball? It turns out you all already have one. We're just not used to think about it that way. I'm talking about this. I'm talking about our version control data. And you see a really simple example from Git here. Version control data is an informational goldmine. Not only does it know exactly when each change to the system took place, which gives us a time dimension and let us calculate a lot of interesting things and statistics, it also knows exactly who did each change. So that means version control data is actually social information. So let's see what kind of value we can pull out of our version control systems. Let's embrace version control data, and let's see how it helps us identify code with the highest interest rate. Now, the concept I use to reason about code with higher interest rate is something I call a hotspot analysis. So let me show you how that works. What you see here is a hotspot analysis of a well-known, mature Java code base, Tomcat. Has anyone worked with Tomcat? Yeah, some of you. Cool. So it's been around for a long, long time, has a very rich history. Now, let me show you how this hotspot analysis works so that you know what you see. First of all, you see that there are a number of large blue circles, the ones that blink on screen right now. Each one of those represents a folder. And you see that you have other circles nested inside them. So those are subfolders. So this is a hierarchical view that follows the folder structure of your code. It's also interactive, which means you can zoom in on the areas of interest in your code base. And when you do that, you will see that each file is visualized as a circle too. And you will see that the circles have different size. That's because size is used to represent code complexity. Now, what is code complexity? Well, it's basically how hard this code is for a human to understand. So how can we measure that? Well, we have a bunch of different ways of doing that in our industry. We have things like McCabe's cyclomatic complexity, we have Halstead's volume metrics, and so on. And you can basically use any metric you want because what they all have in common is that they're equally bad. It turns out that the number of lines of code is an equally good predictor on the code complexity as those more elaborate metrics. So that's what I tend to use. It's the simplest thing that could possibly work. Besides, this is not the interesting dimension. The interesting dimension is this. How often do we actually need to work with that code? And that's something we can pull out of a version control history. We can pull out the change frequency of each piece of code, and we can use that as a proxy for interest rate. And the interesting thing is when we combine these two dimensions, we can suddenly identify an overlap between complicated code that we have to work with often. And that's our hotspots. So let's return to Tomcat. And when we do that, you see that the hotspots are relatively few in a fairly large code base. So now, just because something is a hotspot, that doesn't mean it's a problem. What it means is that that code is a little bit extra important to you from a productivity and quality perspective. So that's the part of the code you want to ensure it's clean, simple, easy to understand, and easy to evolve, because you're going to spend a lot of time there. However, in practice, more often than not, I have found that the opposite is true. And that makes hotspots excellent refactoring candidates. And there's a fascinating reason why that's the case. And I want to show you that reason by borrowing a quote from Mr. George Orwell. You all probably all remember his famous quote. George Orwell once said that all code is equal, but some code is more equal than others. Now, what did he mean about this? Well, I'm going to show you. Have a look at the following graphs. They all show exactly the same thing. Here on the x-axis, you have each file in the system, and they are sorted according to the change frequency. That is, how many commits have you done to that particular file? And the number of commits is what you see here on the y-axis. Now, so you have examples from 3 radically different systems, implementing different languages, targeting different technologies, different domains, done by different organizations, different people. Everything is different. Yet, do you see any similarities here? Do you see any patterns? That's right. They all show exactly the same thing. They show a power law distribution. And this is something I've found in every single code base that I've analyzed. This seems to be the way software evolves. And this is important because it gives us a tool to prioritize. Because what this means to us is that most of our code is here. It's in the long tail. It's code that we rarely, if ever, touch. And most of our development activity is here in a relatively small part of the code. So that's where we want to focus improvements and be pretty sure that we get a return on that investment. So hotspots are a great starting point, but sometimes they're not enough. And I want to show you an example on where hotspots don't work. And I want to show you that by switching code base. So now we're going to look at a completely different case study. We're going to look at the .NET Core Runtime from Microsoft. So how many of you run Windows on your laptops or develop for Windows? Yeah, so I think that's a majority of the audience. So this is what you have running on your machine. Now, this hotspot analysis is something I did 6 months ago, maybe. And at that point in time, most of the hotspots in .NET Core were here in the JIT package, the just-in-time compilation support. However, there's also a very interesting hotspot. It's like a satellite over here. That one is called gc.cpp. That's the .NET garbage collector. And gc.cpp, I'll tell you this, right? It looks quite innocent there on screen. But that's just because the scale of .NET Core. .NET Core is huge. What you see here on screen is approximately 4 million lines of code. And gc.cpp is a big, big file. How big? I have no idea. So let's look it up on GitHub, shall we? Here we go. Whoops. It turns out that that file is simply too big for GitHub to visualize. So we need to look at the raw file, and when we do that, we see that gc.cpp is a single file with 37,000 lines of C++. 37,000 lines of C++. Are there any C++ developers in the audience? Oh, a few of you. That's great. I used to be a C++ developer. I did C++ for 10 years. And yeah, I know what the rest of you are thinking. Like, that's 10 years I never get back. But the reason I tell you this is because I can really appreciate the horror of looking at 37,000 lines of C++ at once. It's scary. And besides, how useful is it to know that gc.cpp is a hotspot? How do you act upon that information? The answer is you don't. We need much more detailed information. So what I suggest is this. Once we identify those big hotspots, what we do now is that we simply take the file and we parse it into different functions. And then we run exactly the same analysis, but on a function level, right? So now we'll look at which functions are actually hit by the different commits. And when we do that, we can start to reason about hotspots on function level. Let's see how that looks for gc.cpp. So when we do this on gc.cpp, we see that the number one hotspot function is a function called grow brick card and tables. It's a function with 332 lines of code. That's quite a lot for a single function, isn't it? It is, but it's much less than 37,000 lines of code, which was the size of a total file. And it's definitely less than 4 million lines of code, which was the size of a total system. So even more important, we are now on a level where we can act upon this information and do a focused refactoring based on how we actually work with the code. So we're going to return to the hotspots in a few minutes, but before we go there, I would like to know, how does it happen that we get a file with 37,000 lines of code? Have a look at this book. This is my book tip to you. So this is really something you should wish yourself for Christmas because it's a great book. It's my favorite book on how organizations failed. It's called The Challenger Launch Decision, and it's written by Diane Vaughan. Now, the interesting thing is Diane Vaughan, she isn't a programmer. She's a sociologist. And she has coined a term called the normalization of deviance based on her case study of the Challenger accident. So how many of you remember the Space Shuttle Challenger? So like 1/3 of you, those are as old as me, remember it? It was back in 1986. So let's do a quick recap here on Challenger. So what you see over here is the Challenger space shuttle at its final launch. So this is the actual space shuttle. This is a huge tank with rocket fuel. And this object here is one of the solid rocket boosters. Now, those solid rocket boosters, they are huge, huge objects. So they are delivered in 3 separate segments that are then assembled before launch. Now, do you see this puff here of gray smoke? Not a good thing. It's not supposed to be there. So what actually happened was that one of those joints in the solid rocket booster, it leaked and hot rocket gases escaped from the booster and impacted the structure and compromised the whole spaceship. So the space shuttle just disintegrated once it got into the air. The interesting thing that Diane Vaughan writes about in her book is that already back in the 1970s, during the early design tests, they noted that the performance, the actual performance of those solid rocket booster joints deviated from the predicted performance. Now, what do you do when you make such a finding during your tests? That's easy if you're NASA. You form a committee. So they did. And they discussed the problem, and they decided to pass it off as an acceptable risk. Years later, during the first in-flight tests of the space shuttle, again, they noticed that the performance of the solid rocket booster joints deviated from the predicted performance. So again, they discussed the problem and passed it off as an acceptable risk. And it went on and on and on like that for years before, on the very eve of the launch, there were some very valid concerns raised about the safety of those solid rocket booster joints due to the unusually cold temperatures in Florida at that time. Again, it was discussed and passed off as an acceptable risk. And the consequence was a tragic loss of human lives. Now, this is what Diane Vaughan calls the normalization of deviance. Each time you accept a risk, the deviations become your new normal. You get a new point of reference. And the reason I find this interesting is because it has nothing at all to do with space shuttles. It's about people like us who develop software. And we have plenty of normalization of deviance within the software industry too. So let's say, for example, that you inherit a file with 5,000 lines of code. That's quite a lot for a single file. But if you work with that file long enough, you become familiar with it. It becomes your new normal. And I mean, besides, seriously, what difference does it make if you add 100 extra lines of code to it? So soon you have 6,000 lines of code, then you have 7,000 lines of code, and so on. And we need a way to fight, to detect, to stop the normalization of deviance. Here's one technique that I found really, really useful for software development. This is something I call complexity trends. So here's how it works. So what I do now is that when I detect a hotspot, I pull out each historic revision of that code, and then I measure the lines of code and the code complexity using any arbitrary complexity metric, such as cyclomatic complexity, and plot the trend over time like this. Because you see, all systems tell stories. We just need to learn how to read them. So in this particular example, what we can see here is that it starts out in 2016. And we see that it grows in complexity, and we seem to have done a refactoring here in mid-2016 that reduced the complexity of that file. But we probably failed to address the root cause, because pretty soon the complexity creeps back in again, before here at the beginning of 2017 there's a very steep increase in complexity, which is a clear warning sign that we need to take a step back and have a look at that code. Does it really evolve in the direction we want it to, or are we creating technical debt here? So the normalization of deviance is one reason that whistleblowers are so important to an organization. And I have found that complexity trends make great whistleblowers in code. So to sum this up, hotspots help us identify code with the highest interest rate. And the reason they work is because all code isn't equal. Now, I want us to climb the abstraction ladder and see how we can use similar techniques to reason about whole systems, whole software architectures. And as you all know, you cannot really talk about software architecture without mentioning art. So, have a look at this artwork. How many of you recognize this? None of you. That's really, really good, because this one doesn't exist. This is something called a liquid crystal light projection done by the artist Gustav Metzger. And the fascinating thing with this liquid crystal light projection is that it changes all the time. So this art looks completely different today than it did yesterday. And the interesting thing is the way it evolves. Because the way it evolves is that it necessitates the destruction of an existing form for the creation of a new form. And I'm pretty sure that that's exactly how code should evolve. But it rarely does. Because successful code will change, it will evolve, and that's actually a good thing. The reason I say that code is auto-destructive is because there are so many code bases where new features and changes become increasingly more difficult and expensive to implement over time. And we need a way to detect that and focus improvements. And again, we have seen the hotspots, right, on a file level and a function level. But in a large system, that's not good enough. We need higher level abstractions where we can start to reason that serve as entry points for us. So what I suggest is this. Instead of measuring things on a file level, we measure on logical components. What is a logical component? Well, I would say anything that carries an architectural significant context within your system. So the way I do this is that I take groups of files and aggregate all their contributions together. And in many code bases, you can basically just follow the folder structure of your code base, because it typically carries some kind of architectural significance for you. And once you have done that, we can start to measure things on the level of logical components. Let me show you a few examples and try to clarify this. I would like to start by looking at a typically service-oriented architecture. And when we do that, this kind of information will help us answer one of the big questions we have around microservices. This is a really important question. I mean, many flame wars have been fought over it, friendships have been ended. And that question is, how big is a microservice supposed to be? 100 lines of code? 1,000? 2,000? Yeah, I mean, we all know it's a bit misdirected to reason about microservice size in terms of lines of code. Because what we're actually after is behavior. We want each microservice to implement a single business capability. So the key here is cohesion. Now, we can start to reason about microservices and answer questions like that if we have cohesion by performing a hotspot analysis on this level. So I basically group all files belonging to each service and do a hotspot analysis on that level. So I'm going to show you some data from a real-world system, a real-world microservice architecture. So now each hotspot here is an actual microservice. And we see that the number one hotspot is something called the recommendations service. that consists of around 5,000 lines of code. And just as we can scale up the hotspots, we can scale up the complexity trends and look at the complexity trend of an entire service. And we see that this service evolved rapidly during the initial development and now seems to have stabilized at a very high level with 5,000 lines of code that changes rapidly. Now, this kind of analysis doesn't really solve any problems. What it does is that it helps us ask the right questions. And this question is, if this service with 5,000 lines of code that changes all the time really implements a single business capability, or if it represents code that perhaps is better off when split into 2 or maybe even 3 separate services. So this kind of data can guide us towards more cohesive systems by focusing on where it actually pays off. But we can do even more with this information. And to show you how, I would like to introduce a new concept for you. It's a concept called change coupling or temporal coupling. And it's kind of different from the way we developers typically talk about coupling, because temporal coupling is invisible in the code itself. It's something you can only see from the evolution of code. So here's how it works. Let's say we have this simple system with just 3 separate subsystems. The first time we do a change to it, we modify the fuel injector and diagnostics module together. The second time we make a change, we modify something else. The third time, we're back to modifying the fuel injector and diagnostics module together. Now, if this is a trend that continues, there has to be some kind of relationship between the fuel injector and diagnostics module, right? So, by using this kind of data and applying them to architectures, we can actually see how well the actual change patterns matches our expectations. I'm going to show you a bunch of examples here, and I would like to start with layered architectures. And the reason I want to start with layers is because they are so immensely popular. So, when I come to a new client, I always ask them, what kind of architectural pattern do you use? What kind of architectural style do you have? And a lot of companies, they tell me, we have a model view controller or a model view presenter or a model view model, some kind of variation on the layered, on a layered pattern. And then you look at the code, and that's never what the code looks like, right? So let me show you what I mean about that. So here are the 3 typical canonical layers in a model view controller. But we all know that we must have a services layer, right? So let's introduce that too. And we all know that we must have a repository layer. And the reason we need a repository layer is simply because, well, I actually never came up with a good rationale for that, so let's just call it a best practice. And of course, below that, we want the object relational mapper so we don't have to access the SQL directly, and then maybe we have some SQL at the bottom. And of course, you know that in reality, you tend to have even more layers. Perhaps you have view helper layers, and what else, right? So 10 to 11 layers is actually not that uncommon. Now, if we want to analyze a layered architecture like this, we consider each layer a logical component and perform a temporal coupling analysis on that level. And when you do that, you will see that in the majority of cases, your change coupling will look like this. In fact, I've found that somewhere between 30 to 70% of all commits touch multiple layers. And this is really, really interesting, because what this means to us is that few changes are local. The majority of our commits will slice through the entire architecture. And there's a very good reason for this. The reason for this is because what you have here in your layered architecture, that's a technical partitioning. It's an architecture oriented around technical building blocks. But the work we do is feature-oriented. It's oriented around end-user requirements. So there's a very obvious conflict between what the architecture looks like and the kind of work we do. And I find it interesting because one of the common motivations behind layered architectures is a separation of concerns. But I will claim if our change coupling looks like this, that it ripples through the entire stack, maybe it's the wrong concerns we're separating on. And I have seen layered architectures work really, really well for small teams. And again, this is where we may get into trouble with layered architectures. It works fine for, let's say, 3-4 people, but if you scale up to a large organization, the consequence of these change patterns will be that you will have basically the entire team working the same parts of the code all the time. And that put us at risk for things like conflicting changes and unexpected feature interactions. And this may be one of the reasons to the recent popularity around microservices. So, as we all know, this is what microservices look like in PowerPoint. In reality, they are much, much more complex, because we know we may have shared building blocks, service templates, client APIs, cross-cutting concerns like monitoring and diagnostics, and so on. So, although that additional complexity put us at risk of violating one of the most important principles behind microservices, and that principle is loose coupling. Because the moment we start to couple different services to each other, their lifetime, we lose most of the advantages of microservice architecture, and we are simply left with an excess mess of complexity. So if we have an important, vital principle like loose coupling, why don't we supervise it using temporal coupling? So again, consider each service a logical component, and then do a temporal coupling analysis on that level, and watch out for patterns like this that cut through multiple services. If you use temporal coupling like this as a safety net, you will be able to detect potential problems like that early, which helps you avoid what I call the microservices shotgun surgery pattern. And the microservices shotgun surgery pattern, that's simply when you want to tweak a single business capability and you end up modifying 5 different services. And there are several reasons why that may happen. The most common reasons I have seen is, first of all, that different services may share code that itself isn't stable from an evolutionary point of view. Another reason may be because some services are just leaky abstractions. The APIs aren't correct. So they expose implementation details, and other services depend upon those details. And now you have tied their lifelines to each other. And I've also seen that this becomes more common when the same team is responsible for multiple related services. All right, so what tools do I use to do all this analysis? Well, when I wrote my previous book, Your Code is a Crime Scene, there were no tools available that could do this kind of analysis. So I decided to implement a simple proof of concept that I open sourced as CodeMat. So it's available on my GitHub. It's capable of doing the hotspots and the temporal coupling stuff. And it may be a good starting point if you want to play around with these techniques. What I'm working on right now is something called CodeScene. So CodeScene is something you can have a look at CodeScene.io. It's my attempt at automating all this stuff. So it's basically press a button and get all the results. There are other options too. There are some options from the academic world, and my personal favorite has to be the Evolution radar, which is particularly strong on temporal coupling. And then finally, as the fourth option, if you want to implement your own analysis, I recommend that you have a look at the Moose platform. So the Moose platform is a framework for building code analyzers, and the Moose platform is also the best excuse I know for learning to program in Smalltalk. It's a great programming language, trust me. All right, so to sum this up, you're going to get some links at the end too. So to sum this up, we have seen that hotspots scale to an architectural level and help us reason about the evolution of our architecture. And we have seen how temporal coupling help us evaluate the change patterns we do to our architecture and how well they fit the actual work we do. Now I want to spend the final minutes on this presentation on exploring the social side of our code, the dimension that's invisible. Before I do that, I would like to ask you, how many of you develop software as part of a team? So yeah, that's virtually everyone, maybe 1 or 2 exceptions. And that's really common these days, right? We have to do it because we take on larger and larger problems. Our systems become larger and more complex, and there's no way we're able to pull that off ourselves. So we need to organize into teams. However, what we rarely talk about is that teamwork always comes with a cost. And that cost is something that social psychologists refer to as process loss. Now, process loss is something that social psychologists themselves have stolen from the field of mechanics. And the idea is that just like a machine cannot operate at 100% efficiency all the time due to things like friction and heat loss, neither can a team. There's always a price for teamwork. So let me show you how it works. Let's say we have a bunch of individuals here. Together, they have a potential productivity. However, that's never what you get out of a team. The real productivity is always a bit smaller, and part of the potential is simply lost. Now, what kind of loss is that? Well, it depends on the task you do. But I would say in complex, interdependent tasks like software development, most of that process loss is probably due to communication and coordination overhead. And the bad news are that you can never, ever eliminate process loss entirely. The trick is, of course, to minimize it. So let's explore it in more depth with a specific example. One of the common reasons for process loss in software that I have seen is something called the diffusion of responsibility. This is another principle from social psychology. And the diffusion of responsibility is something that you may have witnessed if you're unfortunate enough to witness an accident or an emergency. Because it turns out in those situations that the more bystanders, the more witnesses, the less likely that an individual will offer help. This is actually quite scary, but it's a well-researched and well-studied principle. And there are several reasons for the diffusion of responsibility. One of the common reasons is, of course, that the more people that are present, the less personal responsibility do we feel to actually help. We just assume that someone else may help instead. Another reason is that what we do in unexpected situations like this is that we look at others and see how they react. And what do we see? Well, they all look calm. So perhaps this emergency situation isn't as serious as I thought myself. In reality, of course, everyone else does the same thing as you do. They look at others, including you, and see that you seem pretty calm. So there are several reasons for this. And I'm pretty sure that it's the same thing with software. Good code is code where you have a sense of personal responsibility from everyone involved. And yes, I'm going to talk about something very controversial. This is something that you're not even allowed to mention this on software conferences. You never speak about this. Really. I'm going to do something crazy. I'm going to talk about code ownership. Yeah. So I want to point out, when I talk about code ownership, I don't mean ownership in the sense of, hey, stay away, this is my code. No, not at all. I mean ownership in the sense that someone takes a personal responsibility for the quality and the future of a piece of code. And that someone could be an individual, or it could be a small team in a large organization. I'm pretty sure there's really no way around it. It's human nature. So if we have an important principle like the diffusion of responsibility, how can we measure it? Well, remember, we're in version control wonderland. So our version control systems know exactly which programmer that worked on which parts of the code. So what we can do now is that we can take those individual contributions and organize and group them into teams. Here's what that looks like. So this is an algorithm that I've taken from a research paper that I'm referenced here at the bottom of my slide. Not sure how many of you that can read it. But the way it works is basically that we look for parts of the code where multiple teams have to work together all the time. And it's not only about the number of teams that work in a part of the code, it's also how diffused their contributions are, right? So it's the same visualization style as we used for the hotspots. only now the color carries a different meaning. The color signals diffusion of responsibility. It signals coordination. It signals potential communication overhead. So the more red something is, the more team works in that part of the code. Now, the problem is that once you have identified parts of the code like this, where multiple teams have to work together all the time, the bad news are that there's no easy solution for this. There's no quick fix. The things I've seen work in practice is that, first of all, you need to look at code like this from a technical perspective, because the main reason that the code attracts many different teams is because it has many reasons to do so. It has too many responsibilities. So identifying those responsibilities and splitting the code based on those responsibilities will not only give your system more cohesion, it will also help to limit the amount of coordination between different teams. Another thing I've often seen necessary is that some organizations may have to introduce a new team to take on a shared responsibility. So there are a number of things you typically do. But we can get even more information using merged control data. We can start to measure things like Conway's law. Here's an example of what that looks like. So this is a different kind of visualization, right? It's the same style, but now each color signals the work of a single team. So the team that worked the most in each part of the code gets the color of that piece of code. And this is an architecture built on a pattern called package by feature. And we see that from the perspective of Conway's law, this looks like nirvana. This is absolutely beautiful, right? Because each team has a clear responsibility and a clear meaning from an architectural perspective. There's very little potential coordination needs here. So this is wonderful. However, I have to make a small confession here. All data that you have seen so far is from real-world systems, except this one. I had to make it up because I'm yet to find an organization that's close. And besides, I'm not sure you want to take it all that way, because I think if you do that, you run into different kind of problems. But I can talk about that after the session. What I want to do instead is to look at a real-world scenario that is unfortunately much more common. So this is the same kind of analysis, but done on a real-world code base. Now, this was a company that wanted to switch to feature teams. So the way they did it was that they took their organization and divided their developers into 12 different feature teams. And at the beginning of each sprint, all teams were assigned a bunch of stories and let loose on the code base. And the data you see here shows the contributions over just 1 month. Now, do you see any patterns in this? It's really, really hard to detect any patterns. I mean, sure, there's maybe 1 or maybe 2 parts of the code that seems to be almost in the hands of a single team, but not really. So in general, what you see here is a collective chaos. This is a coordination disaster. And the reason I say that is because what you have here is 12 teams that works in the same parts of the code all the time, but for different reasons, since they work on different stories. Not only is this going to be extremely expensive, this is what leads you to meeting inflation. It also puts you at risk for missing synergies between different features. That is, missed opportunities to make simplifications to both the problem and the solution domain. And that's really unfortunate. So please, no matter what you do, align your architecture and your organization. Your code is going to thank you for it. So I've come to the end of this session, and I hope you enjoy this journey through the fascinating field of evolving code. Ultimately, it's all about writing better software. Software that can evolve together with the pressure of new features, novel usages, and changed circumstances. And I'm pretty sure that writing code of that quality will never be easy. So we need all the support we can get. And I hope that this session has inspired you to investigate the field in more depth. And if you want to get started with this, I want to leave you with a number of references. I have 2 books about the subject, Your Code is a Crime Scene and Software Design X-Rays, that just came out, where I go into all this kind of analysis and how to act upon the information, how to use it for refactorings. I also blog a lot about this, so if you're interested in that, check out empir.com, the blog there. We'll have a bunch of different case studies and show different applications of these techniques. And of course, if you want to try CodeSyn on your own code base, if you have some open source software or something like that, it's free to use on codesyn.io. So with those words, I'm going to hang around after this session and answer any questions you may have. But I want to say thanks a lot for listening to me, and may the code be with you. Thanks.